Yeah, I don't know how the theme's. It's a bass guitar theme song. There's other stuff going on. I don't know it very well. That was my best impression. I hope you liked it. Welcome to day 2 of getting better at definite integrals. There's really only one concept I didn't cover yesterday, and that's what they call the average value of a function. This is simply defined as 1 divided by, that's backwards, 1 divided by b minus a, integral a to b, f of x dx. So this is the average AVG of f of x on the interval AB. So don't worry about that notation on the right. That's just something I'm talking about. Okay, so this is the average value of a function over an interval. And why do we call this in particular the average value? Well, all we're doing is, if you think about this, this is dividing by the length of the interval. So what does this average value really say? It says that it's basically we're converting we can think about this as converting a curve to an approximate constant, in the sense that, suppose my curve is doing this, and I look at the area here, and it will tell me my average value is maybe like this. This height that would be A and B there. So that height there is the average value, because it would say that this area in yellow is equal to that area in blue. That's how you can think about it. So we're basically turning any function into what would the rectangle look like if you decided to smush the area. Suppose it was made of Play-Doh or something. You decided to smush it into a rectangle, force it to be a rectangle. How high would that rectangle be? And that makes sense why that is what we would call the average value. So that's just something we like to define, and it's something that mathematicians like to use because averages are always good. Sometimes, for certain things, averages are definitely good. So I just have one example problem here, and it's an applied example problem. Because I know we have so many people in the biological sciences here. It says flow of blood in an artery. Problem says, according to a law discovered by 19th century physician Jean-Louis Marie Poiseuille, I don't know how to pronounce the name. I'll write it down for you. I can't pronounce Poiseuille. Poiseuille? Poiseuille? I don't know. All right. So this guy discovered this law about the velocity of blood in centimeters per second are centimeters from the central axis of an artery. So I'll draw the artery for you all. Here's an artery. It looks like a cylinder because blood is flowing through. Let's put blood in this side. Blood's coming in. We have, the artery has walls. So we have this small radius, and we also have a big radius. You'll notice the small radius goes to the middle, to the inner one, little r, and then we have big radius, big R. And the law that is followed looks like V, the velocity of the blood, V of little r equals K big R squared minus little r squared, where K is a positive constant. The problem asks to find the average velocity of the blood along a radius of the artery. Along little r. So this is maybe tricky to think about right away. What is our interval? That's kind of the first thing we have to answer. So we're going to use this average value formulation up here. You just take the integral over an interval, and then you divide by the length of the interval. And here we want to know our interval. What is our interval? Because it doesn't actually tell us. And this kind of goes back to those other word problems where you kind of want to find the endpoints that make sense. We had done that one problem about coughing, and man, that feels like a long time ago. I mentioned the coronavirus, and I said we would all be coughing soon enough. And I sincerely hope that's not the case, even though I joked at the time. But yeah, this is similar. So basically, what is the smallest number r can be? So what is the smallest number little r can be? And I hope you agree with me that for this to make any physical sense, the answer is 0. So I'll call r bottom 0. That would be a completely blocked artery, and then you're going to have yourself a nice heart attack. And what is the largest number? Little r can be. And similarly, I hope you agree with me that that could be capital R, because otherwise you have an inner radius that is for some reason larger than your outer radius, and of course that makes no sense whatsoever. You would have a non-existent artery then, so at most it would have to be capital R. And so this gives us our interval. Zero to capital R, and in reality it should probably be an open interval, but who cares? There's actually a theorem that says the integral over an open interval or a closed interval is the same. So now we can use the average value. Average value formula all the way at the top here. You integrate over the interval and you divide by the length of the interval. to get average velocity equals 1 divided by capital R, right? That's 1 divided by the length of the interval. Integral is 0 to R, that's integral over our interval. And then our function is given right there, k capital R squared minus little r squared. D little r, because that is the variable is little r. Okay, and as always, I want to simplify this the best I can before I work too hard. So I'm going to pull the k out, and I'm also going to distribute, or in some sense expand. I'm going to split the integral at the minus sign, as I always do. And in the first case, it might not look like this, but really that r squared is also a constant. So really this is kr, integral 0 to capital R dr, minus the second one stays the same. And then it's just the regular power rule. So this is just kr little r from 0 to r minus k over r. And then this r squared, of course, uses the power rule, r cubed over 3, 0 to r. And so what do we get? In the first case, we plug in capital R, get kr squared minus kr times 0, minus, in the second case, I'm plugging in capital R, k over r times r cubed over 3. This whole thing's in brackets, minus k over r times 0 cubed over 3. And so the 0 terms are, of course, gone, and we're left with this term. This is really kr cubed, or kr squared, my bad. Kr squared, that's right. Minus, there's an r cubed on top over here, r cubed on top, and an r on the bottom. So that gives me an r squared overall. So this is really kr squared over 3. So I have 3/3 minus 1/3, so I have 2/3 kr squared. So this is kind of the average velocity. In some sense, this is the velocity we could expect blood to travel at if we don't know the thickness of the wall. The arterial wall. Right, this is saying, suppose we haven't run any tests and we don't know exactly what somebody's thickness, arterial thickness is, the wall. We might know their overall radius, but we don't know the thickness of the wall. That means that we can expect that it's going to have this sort of flow rate. And that's why averages are important. In some sense, they're the expected value of something, an average is. So you kind of say, if I don't know enough information to know everything, I can at least expect it to be near the average. That's why it's a good thing to have at our disposal. So that's a fun little problem for all you bio majors out there, or anything related to biology. And then the last thing I want to talk about is I'm gonna restate my priorities for U substitution, because this got brought up to me the other day and it makes a lot more sense. We can really think about four different priorities. So we go in order. So the U for U sub should be, so your first priority is actually the natural log, if it exists. And that's something that I didn't take into account the last time, was that if there is already a natural log in the problem, you want to use that. And then we kind of go back to what our orders were before. So step 2 is a denominator. 3 is the exponent of e to the blank, right? And step 4 is the piece in parentheses. So that's kind of a safer way of thinking about u subs, is if a natural log exists, actually that is what your u should be almost all the time. And this got brought up to me. This is a better way of thinking about it. Yeah, so with that, let's do just one homework problem. Bring it up here. So, for example, let's do the integral from 1 to 3 of the natural log of x plus 3 divided by 5x plus 15 dx. That's not what I wanted to do. Divided by 5x, sorry. An extra term in there. 5x. So in this case, since a natural log showed up, that's actually what we want du. That's what we want u to be. So u is the natural log of x plus 3, which makes, oh, maybe I was right about this. I was right. 5x plus 15. What is wrong with me? Which makes du, it's easy when you're the professor, you just change the problem until it works. Sadly, you guys don't get that luxury. Du would be 1 divided by x plus 3 dx. And does that show up? Not quite, but there's a reason why I had to add that 15 in there. It turns out if I do du divided by 5, then all of a sudden I have 5x plus 15 dx, and then we have exactly what we want. That piece there is that piece there. So then we're good to go. So what does that mean? That means that this integral, natural log x plus 3 divided by 5x plus 15, looks terrible. I'm going to fix that. Dx is actually the integral of u over 5 du, or also 1/5 integral of u du. And power rule is super easy on that. That's just 1/5 u squared over 2, or rather 1/10 u squared, and then we substitute back in u in terms of x unless we want to change our bounds, but I hate doing that. Natural log of x plus 3, it's sitting above. Now we have our bounds of 1 and 3, right? Those are our bounds, 1 and 3. We can just plug them in and be on our merry way. 1/10, that's squared still. 1/10 natural log of 6 squared minus 1/10 natural log of 4 squared. You're good to go. So that's kind of the extra step that I always forgotten about. The natural log if it exists. So your real order for u sub should be natural log if it exists, then the denominator, then the exponent. And I'm going to get rid of that. So It's really natural log of whatever if it exists. Denominator, exponent of e, and then the piece in parentheses as your last choice. So that's actually all I wanted to cover today. Quick day. It's nice when we have 2 days to cover one section in the book, because that always means that the second day is easier. And actually, tonight's homework will be the last one before the exam. So tomorrow we'll have an exam review video, and I'll go over the practice exam with that. And remember, your exam is open book, open notes, and open calculators. So you don't have to worry too much about like trying to memorize absolutely every single thing or all sorts of problems. You're totally allowed to find similar problems other places and try to use those results to answer the questions. So with that, I'll see you tomorrow with an exam review. And otherwise, I hope your homework goes great. Have a good one.